Welcome to today's lesson. We are on Unit 4, Derivatives of Exponential and Sinusoidal Functions, Lesson 4, Rates of Change of the Number e and Logarithmic Functions. Exponential functions occur frequently in various areas of study, such as science and business. We often use exponential functions to model growth and decay situations in real life. In this lesson, you are also going to learn about a new number that is very similar to pi in that it occurs naturally. Let's take a look at this exponential. So what I've got graphed here is f of x is equal to 2x. Okay, so an exponential, the base is constant and the exponent is the variable. So you'll recognize the curve to have that characteristic shape of an exponential function, okay? And in blue, I have a tangent along the curve, okay? So let's move this curve. I'm going to move this curve, okay? And you'll see that I have this other point here that represents the slope of the curve. And what we're doing is we're scribing out a function that is our derivative, okay? So it's going to be the value of the slope. Okay, let's see. Let's just do this so that we can get a nice curve. Okay, so what do you notice about the derivative of an exponential function? Well, you're going to notice that it's also exponential. Okay, so it's also an exponential function. Okay, so let's change our exponential function to be something that is, say, for instance, let's take 3. Okay, so our base of 3. Okay, so you'll see it's much steeper. Again, let's move our tangent along our curve. What do we notice about the function that represents our derivative? Okay, so our red. What do we notice? Well, we notice that it's on the other side of the function, so it's a bit more steep than f of x is equal to 3 to the exponent of x. Okay, so it's a little bit more steep. Notice how much closer it is to the function. Okay, so notice that. So what that means, like if I was to examine this, what that would say to me is that there represents a base. There has to be a base in which my derivative and my function is actually equal. Okay, and if we were to keep going and keep trying this until we got closer and closer, but I think I might spare you the trouble, you would find that there definitely is a base that we can pick, and it's going to be 2.71. And we're going to repeat the steps that we took before, and we're going to scribe out the derivative, and there you have it. You have a function in which the derivative is the same. So the function is equal to its derivative. And this was discovered by a physicist named Euler. So this constant is actually named after him, E. I just want to make the correction that Euler was actually also a mathematician. So he was a mathematician and physicist. So I don't want to get in trouble by all the mathematicians out there by not mentioning that. Anyway, so let's go take a look at our calculator. So on our calculator, we'll have a symbol scripted E. E might be an actual button, or it could be in the notes that are above the button. So in this case, mine is actually in red. You probably can't see it there, but it's in red, and it's a scripted E. And right next to it, I have e to the x, which is the function e to the x. Okay, so you're going to get to know e to the x quite well. For now, let's just focus on e. So in mine, you have to push alpha e, and yours might be different. So you'll see here that's a scripted e, and there is the Euler's constant. Okay, 2.718281828. Okay, I would just be happy with you just doing 2.718. I even used 2.71, but correctly you probably should put 2.718. Okay. With every exponential function, there is an inverse function, and you may have learned this in advanced functions, that the inverse function is called the logarithmic function, or the log of the function. We encounter the function e to the x very often in nature. so often that it would make sense that its corresponding log function would have its own name and symbol. Mathematicians and physicists are often not that creative. So in order to name something that occurs naturally, we called it, or they called it, the natural logarithm. So you might have noticed on your calculator ln, and that stands for the natural logarithm, which is the log function or the inverse function of y is equal to e to the x. All right, so let's take a look at the characteristics of both e to the x as well as ln of x. Let's first take a look at the domain. So over here, I have the graph of e to the x, the exponential, and then is just on the other side of y is equal to x is our inverse function, ln of x. Okay, so notice they are a reflection of each other about y is equal to x. So the domain of e to the x, okay, the domain, we can say that x belongs to the set of real numbers, okay. The domain of ln of x, however, we can say a set of real numbers, but notice that ln of x does not exist for values of x that are negative, okay, such that x is greater than 0, okay. And just to be correct, we're going to put our squiggly brackets, and you notice I'm not very good at making squiggly brackets. So the range for e to the x, y belongs to the set of real numbers such that y, okay, and notice that negative y does not exist for e to the x, it's greater than 0. And here, y for ln of x is exists everywhere. Okay, so if we were to extend these lines, and we're just going to pretend that this keeps going and going, it'll eventually keep rising. Okay, so increasing or decreasing. So e to the x is increasing, and ln of x is also increasing. Okay, so where is the y-intercept on e to the x? Well, it's right here. Okay, so y is equal to 1, and there is no intercept, not applicable. X-intercept for e to the x, there is none, so not applicable, but there is for ln of x, which is right there. So x is equal to 1. Okay, so asymptotes. So looking at e to the x, there is a horizontal asymptote. At y is equal to 0. Okay, so the x-axis. And for ln of x, there is a vertical. For x is equal to 0, so it is the y-axis. Is there a minimum or maximum value for e to the x? So there is no max or min point. Okay, it just keeps sloping. Okay, there is a concavity, but there is no critical point. No, and then same with ln of x. No. So there is no inflection point for e to the x, but it is concave up, and concave down for ln of x. Let's take a look at this simple exercise. I'm going to get you practicing on your calculator, and I want you to punch this into the calculator. Let's take a look at A, B, all the way to E. So evaluate. Looking at A, we have e to the exponent 3. So on your calculator, depending on what you have, mine is e to the x. I'm going to see that little e to the x, okay, which is above my ln button. So I have to push shift, e to the x, which I'll see the e, and 2, which to me looks a little strange, but that's how my calculator works. Yours might look like e, if it's more sophisticated, it might look like that, or e to the exponent hat 2, it might look like that. This is what mine looks like, and that should give you 7.389, and so on. Okay, so I'd be happy with 7.4. Okay, so let's try another one. So e to the negative a half. So e bracket negative 1 divided by 2. Okay, 0.6065. Okay, you want to get the same number, or if you don't get the same number, try different combinations. Maybe you have to put in the exponent first and then push e, depending on your calculator. Okay, let's try C, which is ln. Okay, so mine, the ln button, and there's already a button for it. Okay, they use it so much. So in this case, it'd be ln 10, okay, which is 2.3. Now let's try ln of negative 5. Oh, math error. Okay, so that doesn't work. And the reason for that, if you remember the sketch, when we talked about the properties of ln, the domain of ln, that a negative x does not exist. So it's not within the domain for x to be a negative number. Okay, so the last one, let's try ln e. Ln shift, let's try alpha e. Okay, so ln of e is 1. And the reason for that is, remember that ln is the inverse function of e. So they actually cancel each other out, and they will just give you 1. So just to summarize this property of e, the ln of e to the x will just give you x. So remember, it's an inverse function. So in order to get to the exponent, you must take its inverse. So ln of e to the x will give you just x. Similarly, e to the ln of x will just give you x. Let's use some of the knowledge that we've gained today in an application question. So looking at this example, the population of a bacterial growth as a function of time is given by the equation. So P of t's population as a function of t, time, is equal to 200 e to the exponent 0.094 t, where p is the population after t times, days. A, what is the initial population of the bacterial culture? B, estimate the population after 3 days. C, how long will the bacterial culture take to double its population? And then D, rewrite the function as an exponential function having base 2. Okay, so part A wants to know what the initial population of the bacterial growth is. Okay, one way that you can do this is just simply look at the value out front of the exponential function. So in this case, it's 200. Or we can say that t is equal to 0 for initial. So p at 0 then is equal to 200. E to the exponent 0, okay, which is just 1, is equal to 200. So the initial population is 200, okay? It's 200. So always put a nice statement when you have these problems. B wants to know, estimate the population after 3 days. So we want t is equal to 3. So p after 3 days is 200 e to the exponent 0.094 times 3, okay? And then just work that out in your calculator. And we should get 200 times 1.3257. Okay, let's round it. So it's around 265. Okay, and you always want to round it because it's population, so we can't have half of a bacteria. Maybe we can, I'm not sure. Not a biologist, but I'm just going to say that we can't have half. So therefore, the population after 3 days is 265. Okay. Okay, so let's do part C. C part. how long will the bacterial culture take to double its population? So what we could do, okay, so we take a look at the initial, which is 200, okay? And so to double, it's going to be 400. So P, after a certain time, is 400. So 400 is equal to 200 E 0.094 T. Okay, so will give me now 2 e to the 0.094 t. Okay, notice when we said double, okay, so it doubles in population. So on the left side, the opposite side of the exponential function, we just have whether it's doubling. If it's doubling, then you're going to see a factor of 2. If it reduces by half, you'll see 0.5 and just the exponential function. Okay, so this is the factor. Now, okay, so we want to find t. So in the past, you might have logged both sides. Okay, now we can use something even easier in which we can ln both sides. Now, I always use ln. I don't even bother with logging both sides. In university, you're going to see quite a bit of the ln and e function. So you can get used to seeing it now. So we can ln both sides. Okay, by doing it to both sides, you're not actually changing the equation. Okay, and so what that does is give us ln 2. Okay, so this cancels each other out, and it just leaves behind the exponential 0.094 t. Okay, and then you're just going to isolate for t, which is ln 2 divided by 0.094. Okay, so t, and you're going to have to punch this in your calculator. There's no other way of doing it. Is equal to 7.4 days. So roughly 7.4 days. So therefore, the culture will double after approximately 7.4 days. Okay? So let's take a look at part D. Part D wants us to rewrite the equation with the exponential function that has a base of 2. Okay, so what we can do is P of t, okay, and I don't know if you recognize this equation, but probably from grade 11, 1 plus r t over, and this could be anything, it could be n, it could be h, I'm just going to call it n, we'll call it h, I've already called it h. So basically this is the factor, the multiplication or reduction or reduction factor. This is the variable time, and this h or n, whatever you might have been taught, is the amount of time it takes for one cycle to occur. So if this was, say for instance, the factor a third, 1/3, it reduces every cycle, it will reduce to a third, then this is the time that it takes for it to go through one cycle. And of course, P naught is just the original population or size that you started with. Okay, so in this case, P of t is then 200, and we're going to use the base 2, so it's doubling time, so we can say 2, okay, and that's t all over, well, we know now that for it to double, it takes 7.4 days, okay, there you have it, okay, and that is how we would express the function of base 2. Okay, and that concludes it. Lastly, we just want to check our learning. And so this particular question, we didn't exactly talk about it. We talked about it, but we didn't go through it in detail. So you're going to actually take a look at this in the next lesson, but I would just want to see if you're maybe paying attention or if you can put it all together. What is the derivative of y is equal to e to the x? Okay, and make your selection now. And the answer is C. So what's so special about this function is that it is equal to its derivative. And that's it for today, and we'll see you next time.